So I thought I'd just do a few more calculus examples. So we'll just wait a second here until my cursor starts working. So what I'm going to do is I'm going to do one differentiation problem, meaning starting the displacement, get velocity, acceleration. Do one more acceleration problem. That means starting with acceleration to get velocity and displacement. Let me just stop. Okay, so things are just working now. So you can be given the x displacement as function time, and I'm just going to make something up here. Let's say it's 3t cubed plus 2t plus 10. So that's the displacement as a function of time. Let's say, of course, t has to be greater than 0, greater than or equal to 0. So this is like a third order polynomial. The initial displacement is 10 meters. One thing is, if you look at, if these are in units of meters, this constant is going to have units of meters per second cubed. And this is going to have units of meters per second. And the last is going to have units of meters. And the reason you have these constants with these particular units is because if I have time, say 10 seconds or something, I'll have units of seconds cubed divided by seconds cubed, but leaving me with meters. Here I'll have units of seconds, 10 seconds, seconds divided by seconds is meters, and then it's meters. So these constants have to have units that are appropriate for as the coefficients of the various powers. So we'll put the units in there. So the displacement at, or position at t equals 0 is 10, because these two both go to 0. Now if I wanted to find the velocity as a function of time, what that is the derivative with respect to time of the function that represents the displacement. So I'm taking the derivative. Another way to do that would be x prime of t. And the prime, so it means derivative, because the function is a function of t, then the derivative is with respect to time. So what we do is we take the derivative of each part separately. So we can say v of t is the derivative of this 3t cubed, 3 meters per second cubed, times the derivative of t cubed with respect to t, you would get 3t squared. The second part, you would have 2 meters per second times the derivative of t. Derivative of t with respect to t is just 1. And the derivative of 10 meters is 0. So we can kind of clean this up, and you get the velocity as a function of time is 3 times 3, which is 9. So you'd have 9 meters per second cubed times t squared plus 2 meters per second. Notice if I plug in some value of t, 5 seconds, I'll have 5 squared, but I'll also have seconds squared. So the seconds squared will cancel out every one except 1 second left, so then the units will be meters per second. The units here, meters per second, which are the units for velocity. The initial velocity, which is the velocity at t equals 0 seconds, is going to be 2 meters per second, because you get 0 squared times 9, which is 0 plus 2. Okay, so that's the velocity. The acceleration as a function of time is the derivative with respect to time of the velocity equation. So you could say that's v prime of t. Again, the prime means derivative because it's a function of time. We take the derivative with respect to time. So for our particular case, we go back here to the velocity expression. we take the derivative of this part. This is a constant, so that'll come down without change. So we get 9 meters per second cubed times the derivative of t squared is 2t. The derivative of 2 is 0. So the acceleration as a function of time is going to be 18 meters per second cubed times t. So here the acceleration varies linearly. Most of the time we just look at constant acceleration, where this is negative 9.8 meters per second squared. Again, the units work out because if I plug a time in, 2 seconds, 2 times 18, which would be 36, and then the units will be meters per second cubed times seconds, so I'll get meters per second squared ultimately. So I always have to get units of meters for displacement or position. The velocity, meters per second, acceleration, meters per second squared. Okay, so that's one case. Now, if you start with acceleration, let's say it's negative 2.5 t squared meters for, well, the units. So the units, let's figure out what the units have to be. So the units for this constant are going to be meters per second to the 5th power, to the 4th power. Because if I multiply this by t squared, and I want to know the acceleration at any value of t, I plug in the time plus the units. So 1 second, you'd have 1 second squared, which would be 1 second squared. The second squareds would cancel out 2 of these, so you'd have meters per second squared ultimately. So it's kind of like over here, we're multiplying by t, so we have seconds cubed. Here we have t squared, it'd be seconds to the 4th, so if that's t cubed, it'd be seconds to the 5th. Now, in addition to knowing the acceleration as a function of time, we have to know the initial velocity. So v, we could say v0, which is v at t equals 0 seconds. And we're going to say that's minus 2 meters per second. So that's my initial velocity. And then you also need initial displacement, which is going to be equal to the displacement at t equals 0 seconds. And we'll say that's 5 meters. So what we do is we start it with the acceleration, and we say that the velocity as a function of time is equal to the integral of negative 2.5 meters per second to the 4th t squared, all whole thing times dt. And the dt tells us what we're integrating with respect to, which is time. So when you do this, you're going to end up with the velocity as a function of time is, well, the constant comes out of the integral. You get meters per second to the 4th. The integral of t squared is t cubed over 3. You add 1 to the exponent divided by the new exponent. And then you have this arbitrary constant c, which is related to the initial velocity. So after you've integrated this thing, then you figure out what c is. So we do that by using the initial conditions. So we know that v at t equals 0 seconds is negative 2 meters per second. And then we plug in 0 into here, and you'll see that the first term is 0, because you'll get 0 cubed. So c is equal to, in this case, c is equal to negative 2 meters per second. So then we can write this out in its full form and find out this is called the particular solution, where you have the constant. So you get negative 2.5 divided by 3, units are meters per second to the 4th times t cubed minus 2 meters per second. So you can see if t equals 0, the velocity is negative 2 meters per second, which matches up with my initial velocity. So we're done there. That's the velocity as a function of time. Just like when we went the other direction, the velocity as a function of time was this thing. This 2 was our initial condition. Okay, then the acceleration, the displacement as a function of time is the integral, displacement position as a function of x as a function of t is the integral of the velocity as a function of time, which we now have. So we integrate that, which is negative 2.5 divided by 3 meters per second to the 4th t cubed minus 2 meters per second, whole thing times dt. And that's, again, the dt is to tell us what variable we're integrating with respect to. So you bring your constant out front and the units. You integrate t cubed. Well, the integral of t cubed is t to the 4th over 4. Then we integrate this thing, which is, let me just go back once, check a second here. Yep, okay. So you integrate 2 meters per second dt. Well, the integral of a constant is just the constant times t. And then you have another arbitrary constant, which I'll still call c. You'll see why we do that in calculus. But so the integral of t cubed is t to the 4th over 4. The integral of a constant is just the constant times t. And the integral, you always add the arbitrary constant. So that is x as a function of time. So now we have to use the initial condition, which said that the initial position at t equals 0 seconds was 5 meters. So that's 5 meters. So again, that's the left-hand side. So you get 5 meters is equal to, well, it's this whole thing times t to the 4th over 4, but t is 0, so this whole thing goes to 0. So you get 0 from the first part. You get 0 times that, which is 0 plus c. So c is easy to calculate in these cases, 5 meters. So our final expression for the displacement as a function of time is going to be negative 2.5 divided by 12. That's 3 times 4. The units are meters per second to the 4th times t to the 4th minus 2 meters per second times t plus 5 meters. And you can see if I put any value of t in, the units I'm going to get here are seconds to the 4th, which cancel that with the seconds to the 4th, we're leaving the meters. Here I have t is going to be just t by itself, which is going to be seconds. Seconds cancel out with seconds, you're left with meters. This is meters. If you plug in 0, you get 5 meters, which is what we got. So that's how the integrations work. If you're given the acceleration as a function of time, you need to calculate the other two. You need to have both the initial velocity and initial displacement. When you're doing derivatives and you're given the equation, you don't have to worry about arbitrary constants or anything like that. You just take the derivatives and the other stuff falls out. Okay, so that's all one-dimensional stuff. Now, if you had a two-dimensional situation, what you would have is a position vector. And the position vector, instead of just being a number times I plus another number times j, you have some kind of equation. So you might have 2t squared minus 10t all times I plus 3t cubed minus 5j. So remember, I and j are the unit vectors. So this is my x direction. This is my y direction. And these are functions of time. I don't know what the heck this trajectory actually looks like. We could plot it. And again, t has to be greater than or equal to 0. And yeah, we could plot it, but I'm not going to worry about that right now. So the velocity vector as a function of time is equal to the derivative with respect to time of the displacement, or the displacement vector, which I'm going to use r for that. So you get r vector. And the way it works, and you don't actually do this until you take Calc 3 when you deal with vector calculus, but it turns out it's pretty simple. You just treat each one separately and then multiply it by their appropriate unit vectors. So it's the principle of superposition being used here. So the velocity is a function of time is going to be, when you take the derivative of this part, which you'll get 4t minus 10. So that's because the derivative of t squared is 2t. 2 times 2 is 4, so you get 4t. And the derivative of t is 1, so you get negative 10. And you multiply that whole by I hat, the unit vector in the x direction. And then here you take the derivative of this, which is going to be 9t squared. The derivative of the constant is 0, so you get 9t squared times j, so that's the velocity vector. And then the acceleration vector is the derivative with respect to time of the velocity vector. The thing that makes it a vector is the fact that I've got these i's and j's, and I could put a k on there if I wanted to make it three-dimensional. So the acceleration vector is equal to the derivative of this with respect to time. So we do this one. Derivative of 4t is just 4. The derivative of the constant is 0, so just get 4i plus derivative of 9t squared is 18t times the j vector. So in this case we have constant acceleration in the x direction and linear varying acceleration in the y direction. And so that's all there is. If you go to three-dimensional vectors, two or three-dimensional space, you've got to have the position vector as a function of t, and each component, the I, j, and k directions, have to be a function of time. So actually, I'm going to plot this thing. Just let me write down the r vector. And what we're going to plot is the trajectory. It doesn't really tell us how fast things are moving, but it shows us the path that this thing takes with respect to time. So I'm just kind of interested to see what it looks like. So what we'll do is we'll close this up, and we will open up this graphing program. No, that was the wrong graphing program. So let me click that one. So I'm going to open it up before. So this is a free program. So the way it works is, you don't need to know how to work this. I'm just going to show you the results. Window, two-dimensional, so two-dimensional plot. So there's the two-dimensional plot. Let's zoom out here before we, because I really don't know what this thing. So let's see. Okay, I thought that was going to do something, but didn't. Zoom out. So page down. Just push page down, page down. Okay, so there's the plot, or the grid. And what you do is you go to equation. This is called a parametric equation. The parameter is t. The first one is the x parameter, is the x coordinate. So I put 2t squared minus 10 times t. That's my x direction. And then my y direction is 3 times t cubed minus 5. And in parametric equations, you have to specify the range of t. So I'm gonna do 5 seconds. So we go from 0 to 5 seconds. These are the two directions, and I say OK, and There it is. So that's what it looks like. So here's our initial position, which is -5. It's -5j, 0, I. So it's, and then you can see the trajectory. It starts to go more negative in the I direction, then it becomes positive in the Y direction. So it's kind of almost like a upside down projectile motion to some extent. So we might have a gravity field that's pulling upward instead of pushing downward. And because it said, remember we took the derivative and we said that the acceleration in the x direction was linear, was actually constant, and the other one was squared, I think. No, it's linear. Anyway, so that's how you would do the actual trajectory by using parametric equations. You don't need to know that yet. We'll talk about it briefly in the second semester of calculus.